students are here. So let's start, Andrei.
Okay, thank you. Very good. Thank you
So
for
thank you
me.
very much. So yeah, I'm not introducing you because we follow your book. Everybody knows you, so we feel honored by this class, by having you here. Thank you
Well, thank
so
you so
much.
much. I feel honored, and I wish I was there in person because it's much warmer there than here. So, but with that, I wanted to do two things in this short lecture. Basically, show how you can obtain a basis for what are called atomic limits, and show how you can get um, topology from states that are not atomic limits. So first I'm going to define what we mean by atomic limits. And we're all going to be talking about electronic systems, basically. So electron, one body Hamiltonian. One body meaning that the Hamiltonian looks something like this. I'm going to get a lattice. So I'll have sites R and R prime on the lattice. I'm going to get some probabilities, which we call hopping parameters, between sites R and R prime of orbitals alpha and beta. So this is kind of the most general. So far, I'm just defining the most general electron Hamiltonian that you can have. But mostly what I want to point out is that you can work this out for any lattice in any symmetry group. But I'm going to only particularize to one symmetry group. And that's the symmetry group with inversion. But I hope to convey that the formalism that we're going to use is extendable to any symmetry group. So in nature, without magnetism, so without magnetic order, so no ferromagnets, no antiferromagnets, there are in 3 dimensions, which we won't be talking about. We'll be talking about 2 dimensions because it's easier, but it's very easy to see that you can go to 3 dimensions. All the crystals or all the kind of perfect, no vacancies, no impurities, nothing that can spoil translational symmetry, all the crystals can be characterized by 230 space groups. And in 4 dimensions, it's, I don't know, 18,000. They're always finite in a number of dimensions. You can get the number of symmetry groups in some dimension is worked out as a mathematical problem. It has to do with homology. It's some more complicated thing that we don't need, but we're going to need 3 dimensions and 2 dimensions. And these space groups, they basically have 3 things that characterize them. So a space group is basically characterized by translations. Then it's characterized by point group symmetries. So this is space group and point group symmetries. And then it's also characterized by the positions, which are special positions of high symmetry where atoms can sit in a material. Okay, now I have to figure out how to do a new page on this. Okay, let's see. Sorry, it's an Android tablet that again I got from my student, and figuring out how to do a new page is not easy for me. This is very strange. This is how you know that I'm that I'm above 40.
So it's not an iPad, right?
It's not an iPad, it's an Android.
Yeah,
I
it
left my
sounds
iPad in my iPad is in the US, so
mm.
I don't have an iPad, but I mean I can deal with it by just erasing just erasing the which is very this is embarrassing, but I can assure you that I'm more technologically advanced than this. I just don't want to waste time, although I am wasting time. Okay, so basically, let's see what we mean by this. What we mean is, now I'm going to give you an example in 2 dimensions. So 2 dimensions, and I'm going to go to the first non-trivial symmetry group, which is the symmetry group with inversion. The only symmetry is inversion plus translations. So I have 2 generators of this group. Inversion sends R to minus R, and translation sends R, and this is as a vector in 2 dimensions. Translation sends R to R plus the lattice vectors. And in 2 dimensions, there's 2 lattice vectors, A1 and A2, generically, because I have 2 dimensions. And what I want to show you is that irrespective of the Hamiltonian, so this is kind of like an approach that doesn't take into account Hamiltonians, right? Irrespective of the Hamiltonian, I can characterize bands in this group by symmetry. So if I have I'm going to draw it in 1 dimension, but of course, you can imagine that there's another dimension ky here where the band disperses. If I have a set of bands that does something like this, okay, then I have a full gap here. I can characterize these bands, okay, in this symmetry group without knowing the Hamiltonian. And that's very important because Hamiltonians normally give you energies, and Hamiltonians depend on the details, as I said. So I can have some hopping parameters. From orbital alpha and beta, and I have some probability called hopping parameters, right? But these hopping parameters are basically model dependent in the sense that if I take one material, they'll have some value. If I take another material, they'll have some other value. Okay. And what I want to show you is that there's something that can be characterized without knowing any of these hopping parameters. So this is a Hamiltonian independent approach that kind of basically aims, in the end, the aim of the talk is to see what's universal about bands. So what's universal about these bands that are kind of detached. There's a gap to other bands, detached from any other bands. What's universal doesn't depend on the Hamiltonian, how you can characterize bands in a universal way. And please ask questions if anything, absolutely anything is unclear. Okay, so what I claim is the following thing, that if I take a 2D lattice, so then let's just draw a 2D lattice. This lattice, has the vectors A1 and A2, okay? Or I can draw it in the other direction. So you see it's periodic. The sites on this lattice are periodic with this translational symmetry. But they also have some inversion symmetry, in the sense I didn't draw it perfectly inversion symmetric, in the sense that if I pick an inversion center, meaning if I choose my origin, so let me choose my origin here. If I choose my origin, I can expect that if I have an atom at one position, I'll have an atom at position x minus. Or if I have, say I have an atom somehow, my atom sits weirdly at some other spot in the lattice. If it's got inversion symmetry, I'll have another atom sitting here. Okay, so that's what we mean by having these these symmetries. And what I want to argue first is that we can classify all bands that are atomic limits. And I have to define atomic limit. So if this band is an atomic limit, it will have some properties, some universal properties that cannot change unless this band is not an atomic limit. So we can basically give a characteristic of all the atomic limits in the symmetry group, and in fact in all the 230 symmetry groups, but I'm focusing on this guy. So for example, what's an atomic limit? Well, imagine that on each site, so on this side here, for example, I put an s orbital, and I put also a p orbital. So let me give you an example of atomic limits. The simplest atomic limit is on each site. Okay, so I have a two-dimensional Hilbert space on each site. This is, each site is indexed by position r, which is an integer times the unit vector a1 plus another integer times the unit vector a2, right? This is how I define my crystal. And if I have an S&P orbital, then my Hilbert space on site is formed by the creation operators of the s orbital times the vacuum, which we're not going to write down, and the creation operator of the p orbital per site. So I have many of these, right? I have basically however many sites I have in my system. If it's a thermodynamic number of sites, I'll have 10 to the 23 Avogadro number of sites in a macroscopic sample. I'll have a lot of sites. So it is a huge Hilbert space, but I can write a simple atomic limit that has the following form. So the Hamiltonian of atomic limit is the following. Sum over R, CRS dagger CRS with minus plus CRP dagger CRP. Okay. So let's consider this Hamiltonian. This is the simplest Hamiltonian you can get. And we're going to introduce the concept of Vania states here also. So this Hamiltonian is incredibly simple. The reason for it is that you can see that at 1 electron per unit cell, so each index R, each unit cell R, so this is 1 unit cell, this is 2 unit cells, whatever. Each unit cell has 1 electron. Then it's very convenient, i.e. you save a lot of energy or you get a lot of energy gain to just fill up the s orbital. Why? Because the s orbital has energy -1. So if I fill up the s orbital, if I make the state as a product of all r's, CRS dagger 0, this is a Slater determinant state. Okay, I just put an electron in each orbital. It's in each s orbital. This has energy minus the number of sites in the system, right? Because you take 1 from each site R, you just fill up 1 electron, and everything else that I do, i.e. taking 1 of the s electrons, depopulating it, and filling 1 of the e electrons, raises the energy because 1 of the p electrons raises the energy because the p electrons have energy plus. Okay, let me see if I can figure out this page now. This is really not. Okay, I figured out the page. Very good. So This model with one negative energy per each s electron occupied and one positive energy plus one for each p electron occupied has the following bands. Okay, if you are so of course you learned about band structure. This is the following bands. I can Fourier transform this, right? So I can Fourier transform this. This is if I Fourier transform, if I live on a periodic boundary conditions, I can Fourier transform this, and this is minus CKS dagger, CKS plus CKP dagger CKP. So this is the same thing as basically filling every momentum of each s electron and at 1 electron per unit cell, and not filling the momentum of p electron. So this, the energy spectrum of this is two flat bands, one at -1, one at +1. This is the momentum. And I'm only drawing this, for example, the kx momentum. If I was to draw the ky momentum, I would draw another thing, and there will be two flat bands basically doing this. This was ky. Okay. So if I'm looking at 1 electron per unit cell, then this band is occupied. I'm sitting with my Fermi level in a gap. This band is unoccupied. And at 1 electron per unit cell, I have an insulator. And the moral of the story is to quantify what type of insulator I have here. Well, here by default, this is really simple. The insulator I have here is the most trivial insulator you can ever have. This is a trivial insulator. Why? Because all I'm doing is on every site, I'm occupying an s electron, or for example, an inner shell of an atom. The wave function on every site, since I'm occupying an inner shell, is very, very, it's like basically like a hydrogen atom with some different parameters wave function. But the wave function of the electron is very localized on site. It doesn't leak out very much off site. Okay. And for this particular model, it doesn't leak at all. For this particular model, actually, it's a delta function. Okay. And my electrons are basically just bound to the atoms. Right? So they don't do very much. They don't communicate between sites. They're just bound to the atoms. You see that you can see through them, right? Like crystals that you can see through them. Those are basically the best insulators. Anytime you can see through something, that's how chemists know that there's a huge band gap, right? Every time you can see through something, it's an insulator, and it's very localized. Okay, so this is the simplest insulator, and these wave functions in real space are called Vanier states. And here, the ground state of this Hamiltonian, as I said, at 1 electron per unit cell, is product over all R's, or all the sites in your lattice. You just fill up the s electrons on the vacuum. This is the ground state. At energy minus number of sites. If I take a state, for example, fill all the sites except one, and then fill that site R1 with a p electron, then you're going to get minus ns minus 1, okay, because I'm filling only ns minus 1 sites with energy with s electrons, which have energy minus 1, and I'm going to get energy plus 1 from the p electrons. So it's going to be plus 1. So this has a gap. This is minus ns plus 2. It's a higher energy than the ground state. And this is the gap of the system. This is just this gap. So to excite particles, I need to give an energy of 2, and this is the gap. So the reason why this is the most trivial insulator, why this ground state is the most trivial insulator, is first of all, it's got a gap, so it's an insulator. And second of all, it's basically just putting one electron on each site, and the sites don't communicate between them. There's no base hopping between the sites. Now I can take this Hamiltonian, call this H0, and take a Hamiltonian which is H0 plus, and now I put some small hopping. I make the electrons hop. And if it's translational invariant, then the hopping depends only on r minus r prime. And I make, where alpha and beta belong to S or P, CR alpha, CR prime, C beta. But as long as this T, any of these T's, so I have, I can have many T's, they have to fall off exponentially, okay, as r minus r prime, because the overlap of orbitals between different sites, if r is not equal to r prime, the overlap of orbitals between different sites has to be small, because the wave functions of the orbitals, the atomic wave functions fall exponentially. So this guy is likely large only for, sites r and r prime very close to each other. But as long as this guy is much smaller than 1, i.e. much smaller than these parameters here, then the only thing I'm going to do to this system is to give it a little bit of dispersion. Okay, so I'm going to give it, these bands will no longer be flat, they'll have some dispersion. Okay, some small dispersion. But because these hoppings are much smaller than 1, and this gap was 1, there's no way I can basically make enough perturbation to destroy this gap, okay, or to close this gap. I'm going to make some small perturbations, basically of order T, okay, but there will still be a gap. And what we're interested is the properties of these occupied bands that are insensitive to adding, these type of parameters, hopping parameters. So basically, as long as I don't close the gap, what's universal about these bands? About the occupied bands. And since we started from an atomic limit or atomic insulator, which means the atomic insulator again means each electron is in the occupied bands is tightly bound to the atom. So these are called Vanya states that are exponentially localized. The delta function is the most extreme example of exponential localization. So we're going to ask what is universal about these occupied bands. Now, are there any questions? Does the question make sense of what we're going to ask? Is it too simple, or is it? Yeah, does it make sense? I guess is the.
Yeah.
Okay. Okay, very good. If it's too simple, also let me know. Okay. So what I'm going to argue is that when you have a symmetry, you can obtain a set of universal quantities that describe flat bands, that describe atomic limits. Sorry, that describe atomic limits. Okay, and there's several things that we want about this set of quantities. in other words, if I now take a Hamiltonian that instead of having one s electron here, it has two s electrons per side. So one s electron, and it's got another s electron also, say of a larger, say, I have an s orbital from shell 1 and an s orbital from shell 2. Okay, and a p orbital from shell 1 and a p orbital from shell 2, right? They grow in size, etc. These, if I have 2s and 2p orbitals, okay, each in their shells, I can still make an atomic limit, for example. And let's write down the Hamiltonian for an example Hamiltonian for an atomic limit. This is the simplest Hamiltonian. This is in s orbital in shell 1. Put this at -2 energy, minus s orbital in shell 2. You put it at -2, -1 energy, and then you put the p orbital in shell 1 at +1. So obviously I'm just making up these Hamiltonians, but the purpose of making up these Hamiltonians is that we're not really interested in Hamiltonians. We're interested in universal properties that stay invariant no matter what the Hamiltonian is, unless you close the gap. Okay? So this, for example, this Hamiltonian has one band at +2, one band at +1, one band at -1, one band at -2. If I sit at 1 electron per unit cell, okay, so the filling is dependent on your chemical properties. How many electrons does the atom have? If the atom has 1 electron per unit cell, I sit here. If the atom has 2 electrons, I sit here. Okay, this, for example, is also an atomic limit at 2 electrons per unit cell. Okay, it's an atomic limit where I fill, where my ground state is a product of all the s electrons in shell 1, the product of all the s electrons in shell 2 on the vacuum. Okay, but this is also atomic limit, and what you want is some properties that are additive. So I want properties of the atomic limits. This is an atomic limit. I can now add some dispersion, make them a bit dispersed, but as long as I don't close this gap at 2 electrons per unit cell, I want some properties that describe these two bands universally without knowing the Hamiltonian. But the first property that I want is that this atomic limit is additive. So now you can see basically that I'm getting to some group structure. So you want to basically put materials in some sort of mathematical structure, which kind of follows some sort of an order. And of course, that's, a group follows some order. So it's likely that you'll have some, it's actually not a group. It turns out it's mathematically called a monoid, but we don't need to worry about that. But you want the atomic limit to be additive. In other words, if I have one atomic limit, and this is the atomic limit of the shell 2 electrons, and I have the second atomic limit, i.e. the atomic limit of the shell 1 electrons. Actually, these are shell 2, these are shell 1, but in any case, it doesn't matter. Then the atomic limit of both shell 1 and shell 2 electrons should have the properties that I can infer just from the atomic limit of the first shell plus the atomic limit of the second shell. This kind of like a, and so this is the first thing that I want to do. And now what I want to argue is that in momentum space, one can universally characterize all the atomic limits of a lattice system. And the way one can do that is through momentum space eigenvalues of the symmetry. So let's go to momentum space. So in momentum space, we draw these bands, right? We draw these bands. For example, this was the 1 electron per unit cell, one S1p orbital. This was an S-occupied orbital. This is a p-occupied orbital. P-unoccupied orbital occupied at 1 electron per unit cell. And I want to ask what's fundamental about these states. And what I'm going to argue is that what's fundamental is their eigenvalues in momentum space. And I'm going to argue that there's exactly 8 with, for example, inversion symmetry, there's exactly 8 types of atomic limits, and every atomic limit that you can find in any material has to be a sum of these atomic limits. I'm going to do this constructively. Constructive algorithm. So again, we focus just with inversion symmetry. Inversion symmetry takes R to minus R, okay? And in momentum space, it takes K to minus K, okay? And if I am on a lattice that's inversion symmetric, meaning my inversion commutes with Hamiltonian, I don't know what this Hamiltonian is, okay? I'm not gonna worry about what the Hamiltonian is, and this is kind of the power of the formalism that has to do with these topological indices. You don't need the Hamiltonian. The Hamiltonian will just give you some information about the bands, but all you need is that information about the bands, not the entire Hamiltonian. Okay, so if this Hamiltonian commutes with inversion operator, it means that I can diagonalize the Hamiltonian and the inversion operator simultaneously. So every time 2 operators commute, it means I can diagonalize both of them. So diagonalize both H and I simultaneously. So it means that the eigenstates of the Hamiltonian, I can make them the eigenstates of the inversion operator. Now, we know that the Hamiltonian can be written in second quantized notation as some Hamiltonian that depends on momentum K. It's got some indices, alpha and beta. For example, alpha and beta here were S and P orbitals. And for a translation invariant system, the momentum space is very important because the Hamiltonian becomes diagonal in momentum space. So then it's very easy to just find the energy levels of this Hamiltonian. For example, in our previous example, HK alpha beta was particularly simple, was -1, was minus delta if alpha beta, if alpha was an s orbital, and plus delta alpha beta if alpha was a p orbital. Right, so let's see, where do I have it? I have it here, right? So if I Fourier transform this, I'm going to get ck dagger ck. It was -1 if it's s orbital, +1 if it's p orbital, and in this particularly simple example, there was no hybridization. There was no alpha not equal to beta term. So there are only delta alpha and beta, and it's the +1 and -1. This is a particularly simple example, but other examples, have some k dependence in the Hamiltonian, etc. The Hamiltonians you've learned about have k dependence. Okay, so if I diagonalize, if I have this Hamiltonian, then in the Brion zone, there are several momentas that are where the Hamiltonian commutes with the inversion operator, because the inversion operator takes the Hamiltonian at k to Hamiltonian at -k, right? So inversion, mathematically, you write it down like this. Okay? Because the inversion takes r to minus r, since takes k to minus k, it relates the Hamiltonian momentum k to the Hamiltonian momentum minus k. So once you have a momentum quantum number, this is momentum, inversion relates states at from k to states at minus k. But at k, at some special k points, then the Hamiltonian commutes. If k is special, the Hamiltonian commutes with the inversion operator. And these points are the gamma point, or 0, 0. So because minus 0, 0 is equal to 0, 0, then here the Hamiltonian commutes with the inversion operator. Another special point is pi 0, because minus pi 0 is equal to minus pi plus 2 pi, since I have block periodicity, which you learned about, 0, so it's equal to pi 0. Okay, same thing with 0 pi, and same thing with pi pi. These points in the Brillouin zone, I can classify the bands by their inversion eigenvalue. Okay, so because the Hamiltonian commutes at these special points, it commutes with the inversion operator, I can diagonalize both the inversion operator and the Hamiltonian. I can classify the bands by inversion eigenvalues. Now, what kind of inversion eigenvalues can the bands have? Well, inversion squares to 1. So the inversion eigenvalues, there's only two possibilities. +1 or -1. Okay. So now I want to show you how to see that atomic limits can only have a certain set of eigenvalues. At high symmetry points in the Brillouin zone. And again, this is an example on this particular symmetry group. Inversion is the simplest symmetry group, space group, inversion plus translations that you can have. And I'm going to show you that the atomic limits can only have a certain. As a corollary of that, any band that doesn't have this set of eigenvalues, or any sum of this set of eigenvalues, has to be topological. And this is how topology basically in real materials in high throughput systems is now identified. This is a very useful thing for practical purposes. Okay, so let's again do a two-dimensional lattice. And this is real space. And what I'm showing you right now has the mathematical name of representation induction. It was something that was invented by Frobenius early on in mathematics, when they didn't have computers and they were trying to get representations of high groups from small groups. But it's particularly useful in quantum mechanics, because what we really want to basically identify is bands as representations, right? So I'm going to take a lattice, and I have that inversion, is a symmetry group, and translation by A1 and A2. These are A1 and this is A2. Is also part of the space group. This is my space group. Simplest space group that's non-trivial. Okay, so I'm going to ask what type of localized orbitals can I put on the lattice? And where can I put them? Well, the answer to question number 2 is I can put them anywhere I want to, right? The system can have, as long as it respects inversion symmetry, I can put them anywhere I want to. A crystal can do whatever it wants to, as long as it respects some symmetry. If it's if you do X-ray diffraction and see that you've got a symmetry, the atoms can be wherever they want to be, or wherever, nature puts them, as long as they respect that symmetry. But I argue that there are several points on this lattice that are special. And these points are the points that are invariant under the symmetry group. So I'm going to pick my unit cell to be this one. Okay, very close to this, my unit cell here. I'm drawing the dots. The dots should be actually very close to the line. I'm drawing them a little bit away from the line. And there's many unit cells here. So I can put the atoms here, which I'm going to call 1A. This position, this is crystallographic notation for what's called Wyckoff positions. And it's just some name you don't have to remember, but you can remember 1A. The reason why it's 1 is because there's only one of them. And the reason why it's A is because there's several of them that are a bit different, okay? So if I pick my origin here, always pick an origin of your system, of your coordinate system, okay? This is real space. Always pick an origin of your coordinate system. If I pick my origin here, I ask what symmetries of the group leave this point invariant? Well, there's not many symmetries. For example, translation doesn't leave this point invariant. Translation moves this point here. And then if I act to translation twice in the x direction, it moves it here. Translation doesn't leave it invariant, but inversion does. Okay, so 1A, the symmetry group is inversion. So if I put orbitals here, they better respect inversion symmetry. Now, we already said that inversion has only 2 eigenvalues. So in effect, I can only put mathematically 2 types of orbital. I'm going to call s orbitals the orbitals that are invariant under inversion, i.e. don't change, they're a sphere. And I'm going to call p orbitals the orbitals that change sign under inversion. In other words, s is a scalar, p is a vector, and this is plus minus. Okay, and it's exactly the orbitals that you know in chemistry. Now, normally in chemistry, you know s. Chemists like to talk in the language of the isotropic SO3, is basically SO3 symmetry group. So S, P, D, blah, blah, blah are 0, 1, 2, 3 quantum number representations of the space of the rotational group. But on a lattice, you don't have rotation symmetry, right? Because the lattice has a translation, and you're not in ether. You don't have rotational symmetry. So really, on the lattice, this large symmetry group breaks down to the symmetry group of the lattice. And the only thing that you can do mathematically is define your orbitals by the symmetry group of the lattice, not by this large symmetry group that chemists talk about. So in other words, if I just have inversion symmetry, from a mathematical standpoint, the p and d orbitals will be the same. The s and d orbitals will be the same. The p and f orbitals will be the same. So all the even ones will be the same, etc. So this is one thing that one should remember, that from your chemistry classes, you must lose this SPD wording, because lattices don't have the symmetry, the large symmetry that chemists like to talk about. Okay, so the only thing I can put here, because I only have inversion, are these orbitals. You know, for example, a d orbital, which looks like this, plus minus, looks the same under inversion, because inversion changes plus into plus, minus into minus, so it looks the same. So it's exactly the same as an s orbital under what we call the group representations of this symmetry group. So At 1a, I can just put these two orbitals. So I can have two atomic limits, one made by the s orbitals, one made by the p orbitals. Atomic limits too. Okay. So, for example, if I want to make an occupied band of p orbitals, I just put all the p orbitals at negative energy and all the s orbitals at positive energy. Okay. So these are the two orbitals I just tile my lattice at every site at every site 1a with these orbitals. But there are some other points in the lattice that are special. For example, this point is called 1b. It's mid bond. Now, 1b is not invariant under inversion because inversion maps it to the mid bond. For example, inversion in the x direction maps it at the mid bond. Inversion maps it at the mid bond of the previous unit cell. So it's not invariant under inversion. In the space group, I also have translation. So I can perform an inversion and then act with translation and bring it back to where I was. Okay. So 1b has the symmetry group inversion plus translation. Now, inversion plus translation as a group also squares to 1. And you can convince yourself because inversion times translation, this is inversion, this is translation, inversion, translation, inversion. Okay? Translation, when I act with inversion on this translation, it translates in the opposite direction. So this is translation, transversion to -1, inversion times inversion. Translation to -1 is identity. Inversion times inversion is identity. So translation times inversion also squares to 1. So it's a group that's isomorphic, what we say, it's what we call in mathematics with inversion, but it doesn't have the same elements. It has a translation. Okay. So this is a special point, the 1b on the lattice, because it's invariant under another symmetry group, which is inversion translation. So I can put s orbitals here, and I can put p orbitals here also. Okay, and this is translation in the x direction, right? Because I have to perform a translation in the x direction. Now, let me just erase some of this. Now you can see where this is going in the sense that you can see how many points are special on the lattice. I have another point that's special on the lattice, which is here, which is called 1c, weak opposition. And the 1c weak opposition, inversion maps it here, but translation in the y direction maps it back here. So this is invariant under translation in the y direction times inversion. And I can again put s orbitals here and p orbitals here. And I define them the same as I define them at the origin, plus and minus eigenvalues of this symmetry group, which is translation times inversion, except they're not at the origin, they're at the mid bond. This is called this atomic limit 3, atomic limit 4, atomic limit 5, atomic limit 6. And of course, there's two more. There's two more atomic limits or one more special point. And this is called the 1d weak opposition. And this, if I do inversion, moves here. But now I can translate in the x direction and the y direction. The order doesn't matter. Okay? And I can bring it back here. So this point is invariant, not under inversion, but under inversion times 2 translations. And I can put s orbitals here, which is atomic limit 7, or I can put p orbitals here, which is atomic limit 8. So basically, I'm just building the representations of these groups at these points. These are point groups. They leave the points invariant in the unit cell. Okay, and I'm just building the representations. So I reached to the conclusion that there are 8 atomic limits. Now, what you can ask is, well, why didn't you put, well, I have this unit cell. Okay. Why did you stress about these high symmetry points in the unit cell, like mid bond? Okay. Why can't I put, for example, an atom at some weird position that doesn't have any symmetry? You see this, if I put an atom here, inversion will take it here, but this distance is not a translation. So I cannot move it back. So the symmetry group of this atom is, the point symmetry group is identity. It has no symmetry. The reason why I'm not worrying about these points is that what I've done before is enough to characterize the bands or the quantum states if I put an atom here. Why? Because if I put an atom here, call this atom A, then I know by inversion symmetry that there has to be an atom here, atom B, okay? And then I can take linear superpositions, A plus B and A minus B, okay? And these linear superpositions of A plus B and A minus B, this is exactly like an s orbital at this 1a position, because you can see inversion A plus B, inversion changes A to B, so inversion of A plus B is equal to A plus B, but inversion of A minus B, inversion changes A to B and B to A, this is equal to B minus A, so this is equal to minus A minus B. So A plus B is identical, basically, from group theory as an s orbital at this 1a position, or actually anywhere, 1a, 1b, 1c position. I can do the same. And A minus B is identical to a p orbital at the 1a position. So this is the reason why special points in the unit cell, which are special under a larger symmetry group than just identity, than nothing, i.e., which are special under inversion in this example, take a higher standing and rule the game of these atomic limits. Because if I put another atomic limit somewhere, if I put another orbital somewhere else, not a special point, I can always describe it as an orbital as special point, or a sum of orbitals as special point. So these orbitals A plus A and B at a general position somewhere in the unit cell that's not the high symmetry point in the unit cell can actually be described just as well by 2 orbitals, one s and one p, at this center of the lattice. Okay, so now that we have these 8 atomic limits, I want to show you how you can universally classify them. So the statement that we've made is that there are 8 atomic limits with inversion. So in a system that, say, I have 20 occupied bands in a system, and I know that these bands are atomic, I have to be able to describe them as sums of some of these 8 atomic limits. There's no other way around. So if I have 20 bands, 100,000 bands, 1,000,000 bands, you'll never have 1,000,000 bands, but if I can devise theoretically a system that of any number of bands, if they're atomic bands, i.e. if they're made out of localized orbitals, I should be able to describe them as sums of some or all of these 8 atomic limits. So, if I have 10 bands, I can have 5 s orbitals at 1a, 1 at 1b, 2 at 1c, and another 2 at 1d, etc. They have to have a combination of these. Okay, so the way you can understand what's universal about these bands is now if you try to describe them in momentum space. And this is how we'll go and find out what's topological. And it's going to take 10 more minutes. Okay. And this is the concept of representation. We basically have done the representations of the point group. Now what we want to do is take these s orbitals. So I have SMP here, SMP here. These are the types of atomic limits I can have as the special weak opposition, 8 of them, SMP. 1A, 1B, 1C, 1D. So if I'm sitting at 1A, again, I said that inversion S&P is plus minus S&P. And now what I want to do is go to the Brillouin zone, okay, and find out what are the eigenvalues of these bands at the high symmetry points in the Brillouin zone. So I have these high symmetry points that I've argued gamma, x, m, and y. Inversion also commutes with the Hamiltonian. So if it commutes with the Hamiltonian, bands should have eigenvalues under inversion at these high symmetry points. Okay, but all I need to do to figure out, so for example, this is atomic limit 1, atomic limit 2. So for atomic limit 1, where atomic limit 1 is just having s orbitals everywhere on the lattice at 1A. Okay, I just have s orbitals here. I just pile the lattice. As long as these orbitals are localized, which is by construction, so I've made them localized by construction. As long as these orbitals are localized, they have positive eigenvalue, right, under inversion. And hence, if I Fourier transform this positive eigenvalue, they'll also have positive, their wave function will be, for example, in the case where they're extremely localized, the wave function will not depend on k, okay, on momentum, because if I Fourier transform something that's localized, it will not depend on momentum, right? It will be constant in momentum space, localized in real space. Delta function means constant in momentum space, and hence the eigen values under inversion at all these high symmetry points in the Brillouin zone will be the same as this guy, as plus. The same thing with the second atomic limit from 1A, which is a p orbital. The bands, let me just actually make it a bit more frugal with space. Again, if these are localized, so this is a system with p orbitals here, all over the lattice, okay? These bands have to have minus eigenvalue at all the points in the Brillouin zone because the wave functions basically don't change if they're very localized. But now look what happens in the case of the third atomic limit. I said the third atomic limit is an s orbital at 1b. So it sits here. And I've argued that this symmetry group, point symmetry group, is not inversion anymore, but inversion translation. So now, when I Fourier transform, the representation of translation when you Fourier transform is not identity, right? If we translate by A, the representation of translation is e to the ik times A, right? But e to the ik, basically, if I take A to be 1, right? We work in units where A 1. If you don't, it doesn't matter. Same thing. You just have to keep track of some units. Translation in the x direction is e to the ikx, right? And now the eigenvalues, instead of being plus everywhere, like they were for the s orbital at 1A, are actually e to the ikx. So this x is pi. This is pi pi. This is 0 pi. So the eigenvalues are plus at the gamma point and the y point where kx is 0, but at kx equals pi, e to the I pi is -1. So that's how the eigenvalues go. Now again, if I have atomic limit 4, which is a p orbital at the 1b position. This minus is kept, but this tx gets you e to the minus ikx. And the eigenvalues, you can just compute them. Okay, they're minus at the gamma point, they're minus minus. And here they're plus plus, because minus times e to the a pi gives you the ikx, gives you plus. So now the moral of the story is clear. Then let's just do them. If I have the fourth atomic limit, the fifth atomic limit, which is a s orbital at the 1c, then I have ty times identity times inversion times s orbital is equal to s orbital in real space. When I Fourier transform, I get an e to the iky from this ty from the translation Fourier transform. So this guy is plus plus minus minus, because this is the pi. These are the ky equals to pi. The sixth atomic limit is a p orbital at the C1c weak position. If I Fourier transform, I keep this eigenvalue here, but I get from this guy, and the eigenvalues are minus minus plus plus. Okay, and let's do the last one, the last two ones. Atomic limit 7, which is an s orbital at this d weak position right here. Okay, this is tx ty times an s orbital and times inversion times an s orbital, and the s orbital is defined as the positive eigenvalue of this group. But now when I Fourier transform, I keep this positive sign, but tx ty, the Fourier transform, is e to the ikx plus ky. Okay, so at gamma point, it's going to have a plus. At the m point, which is pi pi, e to the I2 pi is plus, and it's going to have two minuses here and here. And the eighth atomic limit, which is a p orbital at the 1d weak position, has, you keep the minus sign, okay? You keep this minus sign from the p orbital, but then you again get a phase from the translation group, and the atomic limit is minus minus from this minus, and plus plus has these eigenvalues. So now we've characterized in momentum space all the atomic limits in this group. And if you find a band that has, or a set of bands that has some set of eigenvalues that you can decompose into sums of these eigenvalues, then it's an atomic limit. For example, let's just re-put all the atomic limits. I'm going to draw eight Brion zones here. So S at 1a is plus 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 plus, P at 1a is minus 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 minus, S at 1b is plus plus minus minus, P at 1b is minus minus plus plus, S at 1c is plus plus minus minus, P at 1c is minus minus plus plus, S at 1d is plus plus minus minus, P at 1d is minus minus plus plus. Okay, so these are the Brion zones. These are gamma, X, Y, and M. So for example, if I have two occupied bands, and since I have two sets of eigenvalues at each high symmetry point. So if I have, for example, here plus say I have plus minus plus 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 minus. Okay, so I compute their set of eigenvalues on the inversion, and somehow I get this. Okay, so you can do this through initial programs. Then you immediately know that this is an s orbital at 1a plus plus a p orbital at 1D. Okay, you can immediately see that you can decompose the set of eigenvalues like this. So now you get the picture. I can build 3 occupied bands, and if you can find a decomposition in this is basically a vector space decomposition. It shows you that the set of bands are basically vector spaces. Then if your bands have these eigenvalues, then I know they're equivalent to an atomic limit, or to a sum of atomic limits. Okay, so now comes the punchline and the topological indices. Now you notice something about these.
Sorry, can I ask a question?
Yes, please.
What if you there's a way to combine the right side, a different way to combine? I mean, can there be more than one way to make the
that's the left side, you mean, right?
The left side, yes.
Yes, that's a very good question. So the answer is yes. Mm-hmm. And the reason for that is the following. It's a very good question. So
fine.
So in this case, there's no way. In this case, there's no way. Okay, because you can go through this and see basically that there's no way to do this. Okay, in this case. But if I had this, for example.
But there can be some combination of the eigenvalues that.
Exactly. You're dead on.
Okay.
So
okay.
So let's say I have. So normally what we do in like when we try to find topological materials is we run ab initio codes, find these eigenvalues, and then ask, are they an atomic limit? Okay. So say I have 2 occupied bands having these eigenvalues. Okay. Right. So this is case 2. This is the new case, which is what you want, right? So this guy, you can clearly see that it can be made out of plus, 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 minus, 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 right? So this is S at 1A plus P at 1A, right? So this is an atomic limit that's made out of an S orbital at 1A and a P at 1A. But you also immediately can see that it's also identical to, for example, minus, plus, plus, minus, plus, plus, minus, minus, plus, right? If I sum the eigenvalues together, I'll get the same combinations, right? If I don't know which one is higher in energy, I haven't spoken about energy. Does that make sense? This was Ignacio, right? Or who was it?
Yes.
Okay.
That was the
right. So you see now there's 2 ways. So this is S at 1D, and this is P at 1D, right? So you can see there's 2 ways. So the reason for this is that this decomposition is not always unique. And this has a very clear meaning. It's the group theory meaning of hybridization in quantum chemistry. Now, you don't find it explained like this in quantum chemistry, but basically this is what it is. Because what happened here is that if I'm sitting at 1A, right? So I sit at this position at 1A, right? If I have an s orbital at 1A, like here, like in this case, I cannot move it away from 1A, because if I move it away by inversion, I would need to have 2 orbitals. But if I have an s and a p orbital, then I have 2 orbitals, and I can hybridize them and make sp hybridization. And that means I move 1 orbital here, I move 1 orbital here, right? The two orbitals, I can move them away, not 2 s orbitals. They have to be an s and a p, because why? Because as I said, now when I move them away, I made an a and I made a b orbital, okay? These orbitals, their symmetry group is identity, so they actually have I cannot describe them as s and p, but this a and b, a plus b is identical to the s at 1a, and a minus b is identical to the p at 1a. So you see, only s and p, this is why there's no SS hybridization does not exist in quantum chemistry. It's only SP or SP3, whatever, right? There's no PP hybridization. So if I had 2 s orbitals here, I could not move them away, because if I move them away, these A and B orbitals are equivalent to an S and a P orbital at 1A. But if I had an S and P at 1A, I could move them away, right? Now, if I move them away, look what happens. I have a 1A Wyckoff position here, but I have another one here where I move this. There's another A here, right, by translational symmetry. So I can recombine them at the 1D Wyckoff position. You see? So I can recombine them. I can take them away and recombine them there. So that's why these two decompositions are equivalent. Because if I have an SNP on a high symmetry position, I can make SP hybridization and move them to another Wyckoff position or another high symmetry point. Does that answer your question?
Yes, thank you.
Thank you. Very good question. Okay, so what you notice now is that since we have the atomic limits, okay, if there would be a band that would be made that would have, say I do my ab initio and find one band, find a band that has the following. You have to prove that you can find a band that has the following inversion eigenvalues, but this existence proof is easy and I won't do it here. Say I find a band that has these inversion eigenvalues. Now you can see that this has an odd number in the Brillouin zone of negative or of positive inversion eigenvalues, odd number. But you see all the atomic limits, all the limits, or all the bands that come from localized orbitals have to have an even number of inversion eigenvalues, of negative or positive inversion eigenvalues. All of them have, even, whether you look at plus or a minus, right? It doesn't matter. And that's the beauty of universality. So it doesn't matter, you look plus, minus, they all have even number. But if I have a band that has these inversion eigenvalues, it can never be written, never be an atomic limit or an atomic band. And this band is by definition topological. And you can prove that it will have edge states, in this case, or surface states in 3 dimensions that you've learned in your class. So this means that we can define an index. So this band has to be topological. It cannot be written down in terms of these atomic limits. And hence, it means that we can have an index. And this index, a topological index, and this index is a number of negative or positive, it doesn't matter which one you choose. Negative, let's choose negative inversion eigenvalues in the Brillouin zone at the 4 points, 4 special points in the Brillouin zone, mod 2. All of these have this, the trivial bands have index 0. The topological bands have index 1, right? So this is a Z2 classification. And actually, if I add time reversal symmetry, it's the same classification as the time reversal quantum spin Hall state. So I think the time is running out, and I don't want to bore you more, but I hope it's clear that this is a constructive way that you can apply in every group. All you need to do is find the symmetry of the high symmetry points in the lattice, find the orbitals that you can put there. The orbitals are just representations of the symmetry group of the lattice. Fourier transform them, find their eigenvalues in momentum space. These eigenvalues in momentum space will have a structure. In general, it's not going to be as simple as this, but there's a way of basically getting the essential information from that structure, which is basically called the Smith normal form, and it's just kind of matrix inversion. It's basically a form of matrix inversion, only you're not doing matrix inversion over the real or complex number, you're doing it over the integers. And matrix inversions over the integers have very special properties that are very, very nice, and you can find these topological indices for any type of band in any group. And there's not only Z2s, there's some Z12s, there's Z8s, there's Z6, there's many types of topological systems. And then, since you know that this band can never be written in terms of atomic limits, then, and it's topological, you know you'll have edge states or surface states or other type of things that you've learned in your course. So that's what I wanted to tell you about indices and how to construct them algorithmically in every symmetry group. And if you want to learn more, I can send you some references, or William, I can send you some references. So thank you very much.
Thank you so much. Yeah, it was everything very clear, but yeah, everybody is happy because I think that everyone could follow everything very well.
So it wasn't easy.
If you have some time, maybe there are some questions.
Yes, of course.
Armando, please.
I cannot hear you.
Armando, we cannot hear you. Please connect the microphone. He said. Maybe in the meantime, someone else have some question. So Armando. Otherwise, you can write the question in the chat. Yeah, he's writing. He says something. Well, the students, don't you have any questions?
Any question is good. There's no such thing as a bad question.
Yes, please.
Right. So if the band gap can be, so let's start from, for example, it's a very good question. Let's start from bands that have. So let's start from this band. Okay. This is the SNP orbital model that I've made, right? Now so now I can characterize. So I know this is an S orbital at the 1A Wyckoff position. I know this is the P orbital also at the 1A. But now I add some hopping. And you see, since these eigenvalues are different, normally if eigenvalues were the same, eigenvalues have this thing called level repulsion. It's very hard to bring two eigenvalues of the same symmetry close together, but these are different. So what I can do is I can kind of make my model do this. Like change the parameters of my model, do this. Okay. Okay, so this is, I've changed the parameters of the model. This is still P at 1A, S at 1A. But now if I close the gap, okay, so I go through a phase transition. So let's say I'm sitting at some point I have a gap touching point here where this twofold, this is this plus this together. Okay. Here, because the bands at exactly the phase transition, because the bands are not separate, I cannot just describe one of them. But now, say I switch the eigenvalues. So now I've switched through the transition. I've switched the eigenvalues and made this plus. So I keep the gap finite at all the other points, but made this. Okay. So now you can see that this is topological. Odd number of inversion eigenvalues is topological. So what I'm saying is that as long as you don't close the band gap, okay, the states retains its universal properties. In other words, the Z2 index here of this band is 0. The Z2 index here of this band was 0. Here, I cannot define the Z2 index of one band because they're touching together. I cannot separate them. But here, the Z2 index of this band is 1. And the Z2 index of this band is 1. So band touching transition can change the topological index, okay? And the topological feature of the state. The ones before were trivial, the ones above, the ones below are non-trivial. So basically, I want the bands not to close the gap in order to be able to describe them by a topological index. If they close the gap, I can describe and reopen it. I can go to another topological index. Basically, the only way I can switch between topological indices is through a gap closing transition. But the universal property, unless the gap closes. Does that make sense? Thank you.
And Armando wrote his question in the chat. I don't know if you can read it, otherwise.
Yeah, so that's a very good question. So basically, very good question. So if one has topological bands, you can show that you cannot build exponentially localized Vanier states that respect the symmetry. So for example, in this case that I showed you here, actually, these are bands with a Chern number. So in this case, even if I lose inversion, I won't be able to as long as I don't close the gap. But in the general case, if I have an index that basically is defined in a symmetry group, and then that index is non-zero, and I try to build Vanier states that respect the symmetries of the symmetry group that are exponentially localized, I will fail. So if I plug them into Vanier 90 or other programs that try to build Vanier states, what will happen is that the program will either break the symmetry, it will give me Vanier states that don't respect the symmetry of the symmetry group, or if I impose the symmetry, because you can have in-house codes that go on Vanier 90 and basically impose the symmetries of the symmetry group. Then Vanier 90 will fail to localize the Vanier state, so they'll have power loss. So there's a theorem basically that as long as the index is non-zero, you cannot build localized. They have to be power law, localized Vanier states that respect the symmetries of the system in all of these cases. So the answer is thank you.
Any other question? So maybe what happens if you include the spin into consideration in your argument?
All right, very good. So if you could see, so this was what I did here is, of course, just if I add spin, this would just become the Z2 spin index, the Z2 Foucault index, right? So basically, so if you add spin, all you need to change in all these arguments, for example, with inversion, all you need to change is if I add spin and time reversal, So if I add time reversal, then you know that here I'll have S up and S down. Of course, they don't need to have S up and S down meaning Kramer's pair. So the atomic limits will be doublets. So there's still only 8 atomic limits. There's still only 8 atomic limits, but they would be Kramer's doublets of exactly what we had here. So for example, I can just take this guy here, and instead of having this, I'll have a Kramer's doublet S up and S down. Since time reversal commutes with inversion, I can just diagonalize inversion, and an S orbital can never be the doublet of the Kramer's doublet of a p orbital because they have the different inversion eigenvalue. So there's going to be s up and s down, and under inversion there. So you'll just double the entire thing. So the index is just going to be the number of inversion eigenvalues of the Kramer's pair, right, which is the Foucault index. So this is exactly, so in this case, this is kind of like the trivial explanation of the Z2 inversion symmetric Foucault index. But for example, if you go to 3 dimensions, so you try to do the same thing in 3 dimensions, and that's where it gets more interesting. So you can just do this as an exercise for the people in the class. You can do in 3 dimensions. There you'll have, you'll have 1, 2, 3, 4, 5, 6, 7. You'll have 2 to the, you'll have 8. You'll have 2 to the 3. You'll have 8. Where the hell is the 8? All right, in the middle here, right? You'll have 8 maximal Wyckoff positions, 8 positions that are symmetric, and you'll have 8 times S and P. You'll have 16 atomic limits. So at each Wyckoff position, I can have 16 atomic limits. So if you do the same thing that we did now, you'll find out that on top of the Foucault index, which is the Z2 index, you have a Z4 index. And this was the one that was missed, and this is the higher order TI index. This was the one that was missed in, basically missed. So there's not only the Z2 index, there's not only the, even with Kramer's pairs, the same thing. So if you do this thing in 2 dimensions, you don't get much new. It's basically just the Foucault construction of the Z2 topological index, just halved, because I just didn't do it with time reversal. But if I would add time reversal, as Liana said, basically I would just get the Foucault index or the Z2 index of the TIs. But in 3 dimensions, you immediately see, if you do the same thing, that there's a Z4 index, which basically means that having 2 Kramer's doublets of negative eigenvalue is also non-trivial, whereas it's trivial from a Foucault perspective is non-trivial from this extra index. So there's an extra phase, which is the higher order TI phase in 3 dimensions. So that's why this is useful, because it basically gets you a lot more phases. For example, even with inversion, the TI index, the Foucault Z2 index, is not the only one. There's one more. There's the Z4 index. So so if I get Z2 to be 0 but Z4 to be equal to 2, then this is non-trivial. This is the higher order TI state, basically.
Okay, excellent. So, and this applies to the case of the insulators. And can you figure out some sort of a construction like this also for the case of superconductors, taking into account particle hole?
Yeah, so I think Watanabe. So there's papers by Murakami and Watanabe who I'm not sure if if the construction is complete, but they certainly have looked at that. I haven't looked at that, but they started looking at that. The problem with the superconductors is that we can't, with the non-superconductors we can find materials.
Yes.
But with the superconductors, you need to know the gap symmetry. So that's always the hardest part in classifying these things, because classifying is not that big of an issue, but finding the materials.
Yeah, it's
that's the hardest
exercise.
Right, exactly.
Yeah. Okay. Perfect. So, no more questions. So thank you so much again, Andrei. So
thank you very much.
Meet you soon.
Thank you very much. I really appreciate it. And have a good vacation.